Hello again. In this video I'm going to be looking at the Hioki DT4252. A few people had recommended that I run a Hioki meter. The claim is that these are actually a better meter than what Fluke is producing. The primary reason I chose this meter is it's still produced in Japan and the cost was fairly reasonable. If we look at the box, we can see it's for general testing. Super rapid response, strong noise resistance, drop proof from a meter, guaranteed for 3 years. Precision crafted. Let's have a look at it. Looks like it comes with a fairly nice manual. The tips for the leads appear like they may actually be gold plated. Fairly nice leads actually. Not a bad looking meter. Looks like it's built fairly well. One thing I'd like to mention before we get into this too far, I'm actually quite familiar with Hioki. I never owned or used one of their handheld meters, but I have used some of their test equipment. When I decided to run the Hioki, rather than talking to our rep, I just wrote them using my home email address. And sadly enough, they never responded back. The reason I did that is because a standard hobbyist isn't going to have access to a rep. We'll go ahead and take this meter apart and have a look at it. We have the fuse ratings marked on the back. They also list the power on options. Again, looks like a fairly nice construction. Looking at the fuse, it's a Holly, 1000 volts. Looks like 50 kiloamp AC and 30 kiloamp DC. I'm not sure what this residue is, but it's actually fairly tacky. See the contacts on the switch. Not a whole lot of copper in this area. Looking at the current input, see it goes to the one side of the fuse, to the other side, up to this small current sense resistor. Looks like they've stitched several vias to handle the current. Maybe you can kind of see the discoloration here. There's actually an inner trace then that routes down this way into the ground. Looking at the Fluke meters, they always allow a lot of clearance around this current input. Yeah, I don't know if this one's going to be a problem or not. The mask may save them, but you can see the clearances on both sides are very tight. Looking at the voltage input, we can see it goes through this PTC, through a couple high voltage resistors. And then there's a gas discharge tube here, which again you can kind of see it here. There's an inner trace. It routes down this way again to the ground. I don't know if that trace length is going to be a problem. Looks like the input then travels through this via, through this small inductor here, and then routes up to this contact of the switch. It looks like some of these diodes, like this one here, may actually be additional clamps. You can see the solder blob in this area doesn't appear to be the best. It's really filled in there quite a bit. Just not very consistent. Looks like Hioki's own chipset. Not too surprised. You can see some guard traces on here. Let's reassemble it and we'll power it up. It looks like it powers up just fine. Looking at the manual, this meter has an auto hold feature. We look at the cover of the manual, it's dated May of 2015. They show it's designed to conform to IEC 61010. Using the instrument in a way not described in this manual may negate the provided safety features. Besides the auto hold, it also has an input filter. Looks like this can be programmed for a couple of different frequencies. Just see here if we go to AC volts. See, the first time selected it goes off, 100 Hertz, 500 Hertz, and then back to off. Here we can see the two passband filters selected versus being off. This is on page 13 of the manual. During the continuity check, diode test, or measurement of resistance or electrostatic capacity, measurement signals are generated in the terminals of the instrument. Depending on the target for measurement, the measurement signal may cause damage. And we can also see on page 48, the open terminal voltage is approximately 5.0 volts or less. To avoid damage to the measurement object, check the specifications of the measurement object before use. So here they're talking about basically damaging your target device with the meter while doing continuity tests. Good advice. Let's just do a basic checkout of the meter. And we're just going to use our little test box here. Start with DC volts. So this will be a 5 volt signal. Looks fine. This will be a 1 volt AC signal at 100 Hertz. Looks okay. Continuity test. Looks fine. It's a 0.5 ohm. So 1 ohm, 50 ohm, 1K, it's 100K, 1 meg, 10 meg. Looks like it'll read up to a 60 meg maximum. This with 1 nanofarad applied. This will be a 0.1 microfarad, 1 microfarad, and 10 microfarad. And here we have a single diode, 2 diodes, and 3 diodes in series. Looks like 1.5 is the maximum voltage it can read. Most of the meters I've looked at will actually read 3 diodes in series without a problem. The cost of the Hioki DT4252 is about $150. This is a 6,000 count true RMS meter. It has a DC millivolt range. It doesn't have a micro or milliamp range. It does have a bar graph, and it has a backlight. It does not have a temperature input. In that regards, it's very similar to the Fluke 115, which is also a 6,000 count true RMS meter. The cost of the Fluke 115 is $135. It'll be interesting to compare these two meters. To the left of the 115, we have the 17B+. This is a 4,000 count averaging meter. To the left of that, we have 5KY's Fluke 107. This is also a 6,000 count meter, but it's averaging only. Of course, to the right, we have the Bryman. And I also have 5KY's Amprobe AM530. And we'll use this when we look at the bar graph feature. Currently, all 5 meters are connected to a 100 Hertz 1 volt AC sine wave. This is with 10 volts DC applied off of my Fluke reference. This is with 1 volts DC. This is with 500 microvolts applied. This is with 200 Hertz applied. This is with 1 kilohertz applied. And this is 10 kilohertz applied. At 95 kilohertz is roughly where the Hioki starts to fail. You can see at 94 kilohertz it comes in. If I need to look at high frequencies, I'll typically use a real frequency counter and not rely on the meters. Let's have a look at the backlight. See, the Hioki is definitely dimmer than the others. The display on the Hioki isn't very uniformly lit. You You can see it's definitely got two hot spot areas. This is with a 8 volt peak to peak triangle wave applied. We're going to use this to compare the bar graph update rate. We'll zoom into the 4 meters that have the bar graph. You can see all 4 of these meters are tracking quite well. This is with 1 hertz applied. So I know that the response of these 2 meters is not very good. The Bryman's definitely the fastest of the meters that I've checked. So let's just look at those 2 meters. This is with 2 hertz applied. This is with 5 hertz applied. This is 15 hertz. See, the Bryman is still basically reading full scale. This is with 20 hertz applied. See, the Bryman is still basically reading full scale. Next, we'll compare the continuity test for the 5 different meters. This is the Hioki. The Bryman. The 115. The 107. And the 17B plus. And back to the Hioki. For this next test, I have the 2 meters attached to the high voltage power supply. We won't be comparing it against the Fluke 115. It has an upper limit of about 650 volts. So we'll be using the Bryman for this test. And this is the upper limit of my power supply. So roughly 981 volts. For the next test, all 3 meters are attached to the high voltage power supply. And I'm monitoring the output with the high voltage probe, which is attached to our oscilloscope in the back. And I'm currently applying a 30 hertz waveform. And we can see that on the Bryman as well as the Hioki. Both are reading roughly 30 hertz. Scope is set at 500 volts per division. Again, all 3 meters in this case are true RMS. I'm now going to vary the DC bias and we'll see what effect it has on all 3 meters. You can see this is having no effect on the Bryman or the Fluke, but the Hioki is definitely starting to see an offset. And it's pretty significant, about a 5 volt difference. Let's go ahead and bias it negative. There's definitely an effect on the Hioki. We'll go ahead and try changing the frequency. This is 60 hertz, 400 hertz. This is looking at 1 kilohertz. This is at 4 kilohertz, and we can see the Hioki now is reading roughly 2 volts. For the next test, we'll see if the Hioki has any susceptibility to RF. All 3 meters are connected to the Fluke standard, which is putting out about 500 microvolts right now. Looks like the Hioki is not nearly as susceptible as a lot of the meters I've looked at Next we'll be looking at the static discharge test. Again, this will be 5 transients, positive and negative. And again, we won't be looking at the current inputs. It's with 10 volts applied. It's with 1 volt applied. And this is 500 microvolts applied. This is with 5 volts applied at 1 kilohertz. Continuity test seems to work. This is a 10 meg, 1 meg, 100K, 10K, 1K, 100 ohm, 50 ohm, and a 1 ohm. And this is a 0.1 microfarad, 1 microfarad, and 10 microfarad. Here's with a short, 1 diode, 2 diodes, and unfortunately again this meter can't read 3 diodes. So the meter seems to be fine. It passes ESD, no problems. For this next test we'll be using the transient generator to output a 220 volt rectified AC sine wave. And see the Hioki's reading roughly 233 volts DC and 119 volts AC. Next what we're going to do is rotate the meter through the different modes, and then we'll see if it still functions. Okay, I'll go ahead and functional test it. Looks like the Hioki's just fine. Next we're going to be using our generator to apply a 1000 volt transient to our meter. And you can see we have our high voltage probe attached to the output of the generator. Currently a scope set for 100 microseconds per division and 500 volts per division vertical. Just looking at the output of the generator, roughly 1000 volts at 100 microsecond full width half height. We'll be applying 5 transients each, both positive and negative, using each mode of the meter. Okay, we'll go ahead and functional test it. Looks like the Hioki passes functional test. I think what we're going to do is turn the beeper off. So you do that by selecting filter, beep off. So again, this will be a 1.5 kV transient, both positive and negative, 5 transients on each mode. Okay, we'll go ahead and functional test it, but first, so again we're still at 100 microseconds per division, and the vertical is still 500 volts per division, and we can see it's roughly 3 divisions. Alright, the meter passes functional just fine. Next we'll be applying a 2000 volt transient. Alright, we'll functional test it. Alright, looks like the meter passes functional just fine. This is the data I've collected for the Hioki so far. Looking at the continuity test using a 50% duty cycle, I measured a maximum frequency of 3 Hz before the meter starts to skip. The meter actually will read higher frequencies than 3 Hz. It does start to skip pulses though once we get above 3 Hz. With a frequency of 2 Hz, the meter is able to detect a pulse width of less than 2 milliseconds for a short. It has a short circuit detection resistance of 24 ohms. You can see that's very close to a lot of meters. The open circuit resistance is 234 ohms, so about 200 ohms of hysteresis. It has a open circuit voltage of 1.7 volts. It has a short circuit current of 214 microamps, which again is on par with quite a few meters. Looking at the transient testing, the meter was subjected to our ESD test and had no problems at all. It was tested to 1000 volts and had no problems with this as well. And then tested the meter with a 220 volt rectified AC line, and the meter was swept through all of its modes. It didn't have any problems with that. I then did transient tests at 1 kV, 1.5, and 2 kV, and have seen no problems yet. I think this is going to be the end of part 1. So in part 2 we'll continue to transient test the meter till it fails. Later.